So I'm very excited to present our work. Code is not natural language. Unlocks the power of semantics-oriented graph representation for binary code similarity detection. So this is a joint work between Shanghai Jiao University and group and the University of Texas at Arlington. So the first author, Haojie, cannot be here in person, so I will present on his behalf. So binary code similarity detection is a fundamental task that determines the semantic similarity between binary functions. For example, binary code generated from the same source code through different compilation techniques, optimization algorithms, and different architectures, they are considered semantically equivalent or similarity. So binary code similarity detection serves as a crucial component in addressing various important challenges. For instance, consider a scenario where we have a bunch of vulnerable binary functions from closed source of firmware, and we want to see if this vulnerabilities still exist in any other relevant devices. We can first compute the similarities between the vulnerable functions and all the other functions from the firmware. And then for the functions with high similarity scores, we can further investigate them and see if they are vulnerable. In addition, binary code similarity detection can be used to recover binary function symbols, detect software plagiarisms, or license violations. Here is a common framework used by recent binary code similarity detection techniques. First, the binary functions are separately mapped to a numerical vector through a learnable embedding method. And the similarity scores between binary functions are then approximated by the similarity scores of the vectors. The embedding method aims to make sure the similar binary functions are also mapped to the similar vectors. So the embedding method is the major focus of previous works, and it usually leverages neural networks. So existing works can be generally classified into two directions, that is instruction stream-based and control flow graph, or CFG-based. So as shown in the left figure, instruction stream-based approaches take binary functions as they were natural language synthesis and apply natural language processing techniques. On the right figure, CFG-based approaches typically take basic blocks as natural language synthesis and aggregate features or basic blocks through graph neural networks. So here comes the question. Should we treat code as natural language? Our intuition is it might be convenient and intuitive to process code as natural language, but this ignores many code-specific properties. So the previous works and our tests show that CFG, or control flow graph-based methods, are generally more adequate for binary code similarity detection. So these methods are usually more effective than instruction streams-based methods. In particular, for cross-architecture detection, the instruction streams-based methods are either incapable or perform much worse than CFG-based methods. So now let's look at the difference between the natural languages and the assembly languages. So we believe the fundamental difference between natural language and assembly language originated from the fact that assembly languages are mainly designed for machine execution, but the natural languages are naturally developed by humans for communication. So we observe several major differences. First, assembly languages must have well-defined structures, semantics, and conventions in order to be precisely executed in a machine. We can accurately and easily parse the syntactic and semantic dependencies or tokens in assembly languages. However, it is very challenging to do the same thing in natural languages. And second, we found that natural language syntheses are usually linear. However, reordering instructions or moving instructions between basic blocks is feasible, and such techniques are already deployed in optimization algorithms. And third, we found that the composition of natural language synthesis is complicated, while assembly language instruction usually consists of only one verb and one or more pronouns. Right. So this difference suggests that treating code as natural language may not be the best solution. So let's take one more step to see how these differences between natural language and binary code may impede the semantics learning of binary code with NLP-based methods. So this figure shows a typical input representation of NLP-based methods. So these methods consume a sequence of tokens. Abstractly, each token contains two aspects of information, its token content and its position in the sequence. So modifying either token content or token position results in different inputs of NLP-based methods. And if such modification does not change code semantics, NLP-based methods need to learn from that. And the figure on the left shows three trivial semantically equivalent variants that the sequence representation imposes on NLP-based models to learn. So the first variant, as shown in figure B, involves changing the order of instructions. Since the assembly language is well-defined and has a more flexible representation, an instruction can be moved around using well-defined algorithms without affecting the overall semantics. And the second variant, as shown in figure C, this variant shifts a group of instructions by inserting NLP instructions in the beginning, and the positions of tokens are changed while the semantics is not. And the third variant replaces all the usage of a specified register with another one while still keep the semantics. So from this variant, we can see the order, the position, and the use of specified register may be independent of code semantics in some well-defined situations. So for such well-defined situations or rules, if NLP-based techniques want to learn, they may require a lot more additional network parameters and training samples. So overall, we can see that NLP-based methods are more expensive and more difficult to generalize in this situation. So instead of teaching models to learn these rules, it may be more beneficial to recover the well-defined semantic structures and semantics using traditional methods and present them to deep neural networks to learn high-level semantics. So with that, we design a semantics-oriented graph, or SOG, that can capture the well-defined semantics of binary code. So here's our new representation, SOG. First, we believe there should not be a position encoding. It is actually the semantic constraints and relations between instructions matter, not their order. So we use a graph representation. And second, we divide the semantic structures embedded in the binary code into three categories. They are intra-instruction structures, inter-instruction relations, and implicit conventions. So to reveal the calling conventions and their inter-instruction relations, we analyze the necessary semantic constraints on the execution order and the def use relations and represent them as edges in the graph. And this forms the graph shown in figure B. And further, to reveal the intra-instruction structures, we split instructions into tokens and interpret the intra-instruction structure as another kind of def use relations. And this forms the graph shown in figure C. And finally, since the choice of exact registers is independent of semantics, we eliminate them and only keep the data flow. And this forms the final representation shown in figure D. And overall, this representation not only reveals complete semantic structure of the binary code, but also discuss unnecessary semantically independent or irrelevant information. All right, so with the new SOG, we realize it might not be perfect for traditional GNN methods to directly learn on them. So we design a lightweight multi-head softmax aggregator-based GNN method, or graph neural network method. And now let's look at the experiments. So we use a public dataset from a previous study, also published in USENIX Security. And this dataset consists of binary functions from 3 different architectures, 2 business modes, 5 optimization levels, and 8 different compiler versions. So we evaluate the effectiveness of our methods on the binary function retrieval task. And this task aims to retrieve the ground truth function that is compiled from the same source code as a query function in a randomly selected pool of binary functions. We also test 4 different subtasks, including cross-architecture retrieval, cross-optimization level retrieval, cross-compiler and optimization level retrieval, and cross-all variables retrieval. So we compare with 5 recent works as shown in the table. And also the results are shown in the table. So we can see that our method achieves the best performance on all these tasks. And one more thing, we can see our method uses much fewer parameters as shown in the last column than NLP-based methods. So we also test a one-day vulnerability search. We test 12 firmware images from 3 vendors. From this table, we can see our method achieves much higher accuracy over related works for searching both same and different functions. So in conclusion, we developed a semantic complete binary code representation named Semantics-Oriented graph. And we propose a novel multi-head softmax aggregator. And we also demonstrate the effectiveness of the proposed methods through extensive experiments. For more information, please refer to our paper. In the meantime, we have made our artifacts available. And we also published a short version of this paper in the login online. So if you are interested in our work, definitely feel free to reach out. Thank you.